Hello everybody, welcome to the video number 2 of the series how to build yourself a computer. So in this video we're going to see how we can program a read-only memory. If you haven't watched the video number 1, then I recommend you to do that. It's on my channel in YouTube. And in this video we're going to see how we can put stuff here. In the previous video we had 5 bytes of data in this read-only memory. This read-only memory is like a book that CPU, when it wakes up, when it gets the heartbeat from clock, the CPU is going to wake up, and then when it wakes up it's going to read one by one all the instructions from the read-only memory. And these 5 bytes of data, these 5 bytes that we saw, I'll take them, we'll take a look at them once again. These 5 bytes of data represented a computer program, and this computer program, these 5 bytes of data, the first byte and the second byte were 2 parts of the same instruction, and the same can be said about the third byte and the fourth. So these 5 bytes of data, the first one means put to the register A byte that will follow, and the byte that will follow is AB. That is, these 2 bytes mean for the CPU, when it gets these bytes from here, it compared them to the instruction set, and it found that this byte means put next byte to the register A. Register is the place in the CPU memory, so put to the memory byte AB. That's what it did. It put to the memory, to the register A, byte AB. The CPU did this, and the next instruction was output to the data bus this content of the register A, that is AB, and put to the address bus that we didn't use, but anyway, put to the address bus byte 56. And so we had the address bus byte 56 and the data bus, which is connected to here, byte AB. Let's see one, and sorry, the last instruction was stop. Stop and don't do anything else. Let's see the same stuff, the same that we described here in the 3D model. So we have 3 components of our computer and plus output device. We had 3 components, 1, 2, 3, and output device. So when the CPU starts to, here we have legs, as you see we have these pins, we have these pins or legs, and these ones are marked. These address pins, these are data pins, and these are control pins. Some of them we need to connect to plus to the voltage. Some will be directly connected to the plus, because we need to keep them disabled, and that is wait, non-maskable interrupt, and bus request, and why they are disabled when they are positive, because we have slash at the beginning of this name. That slash means when it's positive it's disabled, when it's 0 then it's enabled. So and when the CPU got these second instructions to output to the data bus byte AB and to the address bus byte 56, then it pulled low these two pins when they were usually high, they were usually positive all the time, and now the CPU pulled them low, and we have 0 here, and connected to here, that's counter pin of the flip-flop, and when the flip-flop gets 0 here, that means for him like pressing of the capture button of the photo camera. And what it does when it gets 0 here, it straight away copies, duplicates what it finds on the input to the output, and it's going to hold this input at the output. For example, we have byte AB now, and it's going to come here, and it's going to sit here as long as this pin is positive. When it got negative, when it got zeroed, then the flip-flop copied input to the output, and the CPU, the next instruction was about when the CPU has finished outputting, then it pulls this pin back high, and when it gets high, it's like releasing the capture button of the photo camera, and the picture stays here. The picture that the flip-flop took when this pin was zeroed. So we have AB here sitting, and 56 here that we don't use, and this output of the flip-flop we have right here. It's flip-flop and its output. So let's see, we connect voltage here from there, 4.5 volts for example, and we have AB sitting here. Why I say AB when we have these lights here? Why I say AB? If you don't understand, just watch the first video. And how do we put these 5 bytes? These 5 bytes, how do we put into here? I say this is the read-only memory. That means only you can read from it, not write. But you actually can write there too. But usually we read from it. But for writing, we have to look at the. So let's do this. We put the same bytes to the brand new chip, to the brand new IC. This is the old one, and we have bought a new one, for example, and we need to put the same bytes of data to the new one. Only we will put something different here, that we would be able to see that the difference at the output comparing to the old program. Take it away, remove it from here. So that's our old chip that works. We have 5 bytes of data here sitting, but when we buy a new chip, I will explain what is going on here later. But when we get the new chip, we have it in package. It's coming from electronic store. I don't recommend to buy these things from eBay or AliExpress, because with large probability you will get bad ones, because almost all that I bought from eBay or AliExpress, they were bad, damaged. And these good ones, they are expensive, and you can buy them from for example from Mauser. But you can search for this chip. I have this chip's name in my folder there. You can find required components, and we have it here. That's AT28C256. AT28C256. Yeah, and we want to buy this. I don't know about this web store, if it's good or not, but we definitely have them here. I haven't bought and this when you insert when we have legs like this, that means deep. That reads like deep. That's the package that we want. Deep. And deep package. And we have it here. That's the one that we're using here. And how much it costs? €8.44. It has 28 legs. This is the voltage that it uses, but in the first video we gave it 3.7 volts, and it was quite happy with that, because we were using it for reading, not for writing. For writing we need to have something like 4.5 volts, not less. And that's the first option. I haven't bought from this Time EU web store. I haven't bought anything. I don't recommend. I usually buy it from Mauser, from here. It has the same old chip, like this. And yeah, that's 15 PU. I don't know what it means, but this definitely means that, but this definitely is present 15, or sorry, that's U, that's just U. But looks the same. This must be the same chip as soon as because we have the same name here, AT28C256. It comes with different packages, and this the one that we want, with the legs. So yeah, when we buy this one for almost 10 euros, and maybe for shipping we have to pay, then it comes, we get it in the package. And what we have inside, we have number FF everywhere. Every address of this let's take a look at its datasheet. AT, yeah, this is the datasheet, and we want to see it from manufacturer. That's microchip, that's manufacturer of this chip. This PDF, that's the one. So that's the datasheet that explains about this chip, everything, how to program it, what is it's designed for, its electrical limits. It has 32 kilobytes of data. It can be programmed with 32 kilobytes. That's 256 kilobits. And what it means, we'll take a look. You see, this is our package, not this, not this. We have definitely this slim package with legs, 28 legs altogether. And you see, we have address legs starting with A0, A1, A2, A3. Some of them come here, A8, A9, and so on, A10. Here we have, and the last one is A14. That means from A0 to A14 we have 15 A legs. That's 15 legs. Each one can be either 1 or 0. You can see it from my first video what it means, but it can have voltage or not, 1 or 0. That means if we have 15 legs, and that's we can okay, binary system is like it can be either the same digit. We can have either 1 or 2. For example, we have 0 now, or sorry, we can have either 1 or 0. We have the 0 now at leg number, at leg A0 we have 0. That's our address. Every leg of starting with A has 0. That means for the chip address is 0. And also we have write enable pin inverted. As you see, it has line at the top. That means that write enable pin is activated when it's low, when it's 0, and it's disabled when it's high. And we have write enable, usually we disable it to be able to see the content of the memory chip, and we enable it as soon as we want to write something. We put number here at the data bus, and we put address at the address bus, and the chip will write at the address this byte of data. So it's like a book. Every page has number starting from 0. That is address 0. It has some information sitting inside, and this pin is output enable. When we enable the output by pulling this pin low, then we will get the content of this address. For example, the page number 0 will show up here at the data bus. And we have address number 0. When we add 1, what we get? In yeah, we have 1 at the A0, we have 0 at A1, we have 0 at A2, we have 0 at A4, and all the rest are 0. When we give one more, that means 0 at address A1 and 0, oh sorry, 1 at address A1 and 0 at address A0. All the rest are zeros. If we, but actually it is address number 2. If we add one more, that means address number 3 means that we have 1 at A1 and 1 at A0. If we have 4, that means address number 4 means that we have 1 at A2, 0 at A1, 0 at A0. So that's the binary system, how it works, and you can watch my video number 1 to know the details. And we have 15 altogether. That's the maximum that we can have on these legs, which is the maximum address. 8, 9, 10, 11, 12, 13, 14, 15. That's 15 legs, and when they are all 1, that means the maximum that we can have. And that means 32 kilobytes, 32,000 bytes. Each byte can have its own unique address, and altogether there are 32 kilobytes. That's 256 kilobits. That's what we saw in the data sheet. And so this many bytes we can have at this sitting at different addresses, like in a flat block. We have different flats. Each flat has its number, and in every flat lives someone. And so the same way it's here. Each number that we put inside, for example, number 3E lives at address 0, number AB lives at address 1, and so on. But altogether we have only 5 bytes, so we don't need that many, 32,000. We only need 5. And for that, we can use switch from 1 to 0 only. Let's put 5 here. And as you see, we have only 3 bits that we can switch from 1 to 0. We only need 3 of them to have 5. This is all the rest address bits, address legs can be zeroed. Yeah, and data bus. What about data bus? If you put some address here, for example, we have here 101. That's address 5. If we put to A2 here 1, this goes 0, and this 1. That's 101, like here. That's address 5. And if we put this like the positive, 0, positive, and all the rest are 0, then for memory chip that means address 5. And when it sees that output is enabled, it's low, and writing is disabled, high, then straight away the memory chip gives to the data bus address that it number that it will find living at address 5. Well, let's see, for example, 2. That 2 means 1, 0. 1 we're having at A1, 0 we're having at A0. If memory chip sees this address, all the rest are zeros, only 1 is 1, that's A1 is 1, and if memory chip sees this, writing is disabled, and output is enabled, then the memory chip will give, that's 2, address 2. In our old chip we had at address 2 at 0, 1, 2, leaving D3. If in the memory takes this D3 and puts it, copies it to the data bus. D3 we will find at the data bus. It's hexadecimal system D3. That means this number 11010011 we will find at the 11010011 at these data pins. They are named IO here, but I would name them rather D0, D1, D2, and so on. So you get the idea, yeah? And when we want to write something, we will enable this writing and we will disable this output. If we do that, then the memory will write to the given address that we can set here using ones and zeros. The memory will write to the given address, to itself, the number that it will find here. We will program this. Some we put to 1, some we put to 0, just like here. And then the memory will write this number that we'll set here at the data bus. It will write to this address. So, and we have two more pins here. WCC, that's plus. We have 28 legs altogether, and starting from this, we start counting from this ring over here. You see this ring, over here. Sorry. Yeah, this ring over here, that means the beginning of the chip. We start from here, the reading 1, 2, leg number 1, leg number 2, leg number 14, 15, 16, and till the 28. This 28 altogether, 1, 2, 3, 4, and so on, 28. And leg 28 we are connecting to positive. I don't know why this VCC, what this VCC stands for, but I know that we connect to plus. And this one, ground, we connect to ground. And that is the power supply pins of this chip. So we have address pins, we have power supply pins, we have control pins, writing enable, output enable, and one more pin, sorry, this is chip enable. We keep this all the time low, so we enable this chip all the time. And we have control pins, we have power pins, we have address pins, and we have data pins, 8 of them. And that's it. That's all we have here. If we take a look at the 3D model, we have address pins, we have data pins, we have control pins. Oh, sorry, this is the memory. We have address pins, we have data pins, we have control pins, output. It's output enable, chip enable, it's enabled, writing disabled, it's control pins and power pins. But this we have here, so we disable the writing, it's statically disabled, and we are not going to enable it on the computer, we are not writing anything. And chip enable, if we connect to enable, this is okay, we all the time keep this chip enabled. Power, we connect to the power, ground and plus, and output enable is switching. At the computer sometimes it's enabled, the output, sometimes disabled when the CPU is using this bus to avoid conflict. So we have taken away the memory chip. We want to program something on it, but now we have brand new memory chip. The old one, we already know what's inside. Inside is 5 bytes of data, but the new one, what we have inside, if we buy it from electronic store, we have received it. What we get inside? Inside, by default, we have FF everywhere. We have hexadecimal FF everywhere. In binary, that means this number. You see, all ones. That's address. If you read address 0, you will find this number, all ones. If you read address 1, you will find this number. If you, whatever address you will take until you reach 32,000 bytes, 32,000 addresses, something. All the addresses contain this number. Why? It was programmed this way at the factory. I think it's because they wanted to show that everything works. Every bit is workable. This byte, that means 8 bits. Each one can be 0 or 1. They are named bits, and 8 of them mean bytes. And it's maximum that can have one address of this memory. It's the maximum number. So we have all ones because the manufacturer wants to show you that every bit is working. Every bit is able to hold 1. If the manufacturer if the manufacturer would put 0 here, then you don't know if it is 0 because it's intentionally made 0, or if it just doesn't work. That's why it's 0. So when we get this chip, brand new chip, we all this chip contains these numbers everywhere at every address, and we want to talk with these legs. We want to connect these legs to the plus and to the ground according to our needs. And for that we have this thing. This is the breadboard. These are connected between each other, these holes of the same row, and these are connected between each other, all the holes in the same row. With these metal strips are connected, and with these metal strips, these ones are connected. And if we want to put some voltage from here to here, we need to use bridges. If we put something inside like this, then it will not fall out. Then it it's connected to some strips. Why do we need this? If we put with this, this is the prototype board or breadboard named. It's very cheap, and it's made to make prototypes on it to avoid soldering. Here we have joined all these contacts between each other, all these rings we have joined with solder and with wires. But what if we don't know if it's going to work or not? We better try before we solder something. We try it on the breadboard, we connect it without soldering, and it goes, these legs go inside these holes, and it's going to stick there to it's going to stay there. For example, if we put like this, then if we take multimeter, continuity, yeah, if it's joined, then it gives sound. If we check this leg, you see this leg is connected with this hole. This whole metal strip connects with this leg. What we have inside, we have something like this. The lips, these lips can hold stuff, just like this. They will hold electronic components. Legs, they will hold legs. Yeah. So this is fixed, it doesn't fall out. Now we're going to join we put voltage here 4.5 volts, because as I said, to program this chip you will need some more voltage, not 3.7 volts, but like in the first video, but you will give some more voltage here, 4.5 volts. For example, if you we know that if they are connected, these long strips bring this voltage from here along this line. If we put, for example, probe here, and we'll take from here, if you check, for example, here, you will find 4.5 volts. This goes along this way. So we can take this voltage to, for example, here. Now it's empty. We don't have anything here. It has no voltage here, but we will give it voltage just with bridges, using bridges. We get these bridges from eBay. That's okay. They are so simple things that it's not likely that anything goes wrong with them. But these chips, these integrated circuits, I don't recommend buying from web markets. Better spend some more money, but get the right thing. So these are bridges. This is just metal. Just metal wires. With having different length. If we get this voltage from here, if we get this voltage from here, 0, we connect it to here, that the electric current would be able to flow back. 0 is allowing to flow back. So we have connected 0 with 0. This strip with this strip we have connected to be able to later use it here. And the red one, we will connect with the red one positive with positive. Now what we have done, we have connected this red strip with red. We have directed the current from one side to the other. And we can check it. If we take multimeter and we see 4.5 volts. Now we have 4.5 volts here and here. So let's give food to this guy. We will connect leg number. Where is the data sheet? Let's take a look once again at the data sheet. Leg number 28 goes to plus. Leg number 28 goes to positive, like this. And leg number 14 goes to ground. That's the power supply. Then our integrated circuits gets the power. And we connect this to ground, like this. Here is one you need to danger that we need to address is that you definitely don't want to connect this with ground and this with positive, because you will destroy this chip very quickly. It will get very hot and you will find these amperes growing very rapidly. You will have a lot of amperes. So I have destroyed a lot of chips by connecting them wrong way and spent a lot of money on them. So you want to avoid this. Connect this to ground, pin number 14, and pin number 28 you connect it with plus, it's positive. So it's cold, it's okay, and we have no amperes. That's very good. It has no short circuit inside, so it feels nice. Now it has the power, and now we need to connect all the rest legs. Leg number 1, leg number 2, leg number 3, all of them are addresses A. But we, as you remember, to address only 5 addresses, we don't need this many. We only need 3 legs. This number, if we want 5 bytes, we need only 3 legs to change from 1 to 0 and from 0 to 1. So we need to work only with 3 legs. All the rest are 0. So all this we connect to 0 except for 3 legs, A0, A1, A2. That's 1, 2, 3, 4, 5, 6, 7. 7 legs we connect to 0. So we get the 0. Oops. We get the 0 and we connect to leg number 1. And we have these small bridges. We'll connect leg number 1 with leg number 2. We'll connect leg number 2 with leg number 3, and then leg number 3 we will connect with leg number 4, leg number 4 we will connect with leg number 4 will connect to leg number 5 like this. Leg number 5 we will connect to leg number 6. And then leg number 6 we will connect with leg number 7. So we have 7 legs connected to 0 now. You see, they are connected with each other and go to 0. From 1 to 7. Yeah. 1, 2, 3, 4, 5, 6, 7. Connected to 0. Now, leg number 8, 9, and 10, they are A0, A1, A2. We will connect to 0 as well, but using these longer bridges, because these longer bridges allow us to work individually with these legs later, separately. With each leg, some goes to 0, some goes to 1. So we have A2, A0, A1, A2, the same way connected to 0, but using these legs, green legs, that if we need to change one leg, we just switch it like this, and the same leg gets from 0 to 1. You see, that helps us to change them individually. So we have all these address legs connected, 7 plus 3, and then goes data legs. 3 of them, and here we have 5 more. We want them at the same line here, so we will connect these legs to here, and we want to see what's inside these legs. When the memory chip wants to show us the number sitting at a given address, then we want to see that number when it's being shown. For that, we can use these light emitting diodes, but I have connected them this way. Here, how they're connected, we can see this 3D model, the same 3D model like before. We have this we have 8 diodes. Each has its input and output. Outputs are all connected, and they go to resistor. The outputs of these diodes, these are 8 diodes, they all connected like you see with this metal wire, with this thick metal wire, they all connected, the output of these diodes, and go to the resistor. It looks backward, and from here through the resistor, and from resistor it goes to ground, and to the resistor, all the outputs of the diodes connect to the resistor, and from resistor, from the back side of it, it goes downward to the ground. And these are inputs of the diodes. Each has its own input, just like here. So we want to watch what we have at these pins from IO0, that's D0, to the IO7, that's D7. Data pins we want to watch. That's why we connect them with the inputs of the diodes. And the output of a resistor, the resistor is needed to protect them from overburning. They are greedy. Diodes are greedy. They light emitting diodes. They eat too much current. They eat so much current that it will destroys them. And to limit this current that flows through these diodes, we put resistor like here, like this, and it will limit the current that flows through diodes. Now, we put these diodes this way that we will watch what is, if it has 1, this leg, for example, is 1, is positive, then the diode will show us. So we connect this leg with diode. 5 of them we have here, 3, 4, 5, 6, 7. So we connect straight away here, 5 of them. Sorry, it's different way. That's 3, 4, 5, 6, 7. Just like this. 3, 4, 5, 6, 7. And 3 of them we have at the different side. You see, we have 3, 4, 5, 6, 7 from at this side, but 0, 1, 2 we have at this side. We want to connect them with this 0, 1, 2, with these 3 diodes, the inputs of these diodes. So we that's 0, 1, 2. We connect with 0, 1, 2. That's starting with number 2. Just like this. So now this D2 or IO2 is connected with this strip, and from this strip we will take a bridge to the diode. We'll put a bridge here. So the voltage flows from here to here and from here to here, to input of the diode number 2. So D1 we connect with second diode. Just like this. Now D1 or IO1, leg number 12, is connected from here to here, to this strip, and we need to bridge this to the input of this diode. And we're having another bridge here. just like this. And the last one is D0 will connect with this diode, with input of this diode. I believe we can have this black longer bridge. Like this. Yeah, now we have connected this D0 to here, and from here we'll take to the input of the diode, the first diode, just like this. Yeah, now all the diodes connected, all the inputs of the diodes connected with these data pins. So we can see what's inside when the memory chip decides to show us who is living by this address. Now we have address 0, not all connected. We need to connect them all. Then we'll have address 0, and the memory chip, when the output is enabled, then we will have the resident of this address 0 at the data pin. So now we have connected all these data pins with diodes, but we need to take the resistor and connect it to 0, as you remember. Take we'll take a little bit longer, should be this. Just like this. We have connected the resistor, the output of the resistor with 0, so the electricity now flows from input to output. And don't pay too much attention what we have at the diodes at the moment. We need to connect all the address pins with 0, then we will have correct output. Then we will have, yeah, the right output. So we need to connect all the rest of the legs. We have connected till here. Chip enable we will connect to 0. Chip enable, that's the next pin. We will connect to 0. Using this longer bridge, I think. Just like this. So now we have connected next leg, chip enable, with 0. That enables the chip. And next leg is A10, then goes output enable. Let's connect these legs, control legs first, and then we will connect all the rest address legs with 0. So output enable pin we will connect with 0 because we want the output to be enabled. We will use a longer pin because later we will disable the output. Now it's enabled. It's output enable pin. That's A10, output enable. A10, output enable. And this pin 27 we will connect with plus, with 1, because we want to keep it disabled. write enable is disabled, but sometimes we will enable it. So we will connect write enable with disable. We will disable the writing 27 by connecting it to plus, and now all the rest of the pins are address pins: A13, A8, A9, A11, A10. We will connect them all with 0, with ground. All the rest floating pins which are not connected, we will need to connect. And then we will have defined output at our diodes. We'll give we'll give 0 to A10, just like this, and from A10 it goes to 11, then goes over the bridge, like this, and one more bridge. Then we will have all the pins, all the legs connected somewhere. So 0 goes here, 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 and the last leg that is not connected, we will connect it to 0, its address. Like this. Now we have all the legs connected somewhere to the right places. And what is the state now? The state is this, that we have 0, address is 0, because all the A pins are connected to 0, and output is enabled, because this output enable pin connected to 0, and writing is disabled, because this write enable pin connected to plus is disabled, and we have some output here, but for some reason the light emitting diode number 7, 0, 1, 2, 3, 4, 5, 6, 7 doesn't show anything. Well, let's change address from 0 to 1. Now we have all the ones what we supposed to have. At each address we have all the ones that's designed to be so, but for some reason we have at address 0 we have bit number 7 is not 1, it's 0. Let's make it 1. Let's connect all the pins. Sorry, let's disable the output. If we connect it to plus, Then we will disable it. Output disabled, and we will set number here. We will set all of them to ones, to 1. We'll connect this. We'll connect this to 1. We'll connect actually let's write here this to save the time. We will write here 3e, and how this what this 3e looks like. Let's write the address 0, let it be 3e. Yeah, 3e looks like this. That's 00111110. And since 7 is here at the end and 0 at the start, it's opposite direction. 7 at the start, 0 at the end. So that's 7, 6, these orders 7, 6, and so on. And here it grows, and here it decreases the order. That's why we start counting from the end to the beginning. 0, 0, 1, 1, 1, 1, 1, 0. 0. Yeah. 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 1, 1, 0, 0, 0, 1, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 1, 1, 1, 0. Now we have a number at the data bus, at the data pins. Starting from 7 to 0, they are connected, as you remember, here to the diodes. So starting from 7 to 0, we have a number here, D3, or sorry, not D3, 3E was the number, 3E, that's binary representation, we have set the number here at data bus. Now at the address bus we need to have 0. Address is 0, and now it is 0 because all the address pins, address legs are connected to 0. Now we have disabled the output, so it's not outputting at the data bus, but it's inputting. At the data bus it will read our number, and address is 0. And now we enable the writing. Now we enable the writing for a moment, connected to write, enable, connected to 0, and disable writing, connected to 1. Now what we have to do, we will remove our number from here that we have set at the data bus. We remove it, and we will check what we have written. And for checking, we enable the output like this: 0 0 1 1 1 1 1. Must be 0 here. Oh, we don't have 0 here. We just make a little hack. We connect it with 0. These ones we need to connect to 0 too, I think. Why we have wrong number here? I don't know, because of bad connection maybe, but I hope it will get. Oh, sorry, I had to disable this output before setting the number. I have made a mistake. Now we have disabled the output, and after that I should have set the number, not when the output was enabled. I shouldn't have set the number when the output was enabled. So now the output is disabled. We will connect it with 0. We'll connect it to 1. Maybe this will work, maybe will not work. Let's see. Yeah, we have done this. This pin number 0, D0, is now 0. Why these are ones? Because we haven't connected them to ones. We hadn't connected. They were floating. That's because they were floating. This chip sometimes puts them high for some reason, and we didn't even need to connect them. But the right way to do that is to connect every pin. But we have correct number at the. We have the right number at the address 0 now, and we change the address to 1. If we change the address to 1, then we will have FF in hexadecimal representations that we're supposed to have. Now we will disable the output, and we will set the number at the address 1 that we want to be written. At the address 0 we have 3E now. Now at the address 1 we want to have not AB, it's going to be outputted in our program. We will see this number at the output when our computer will work. So we will change AB. We will put something like, for example, we will put 1 1 0 0 this one, and that means CC in the hexadecimal representation. But in binary we need to connect these data pins according to this number 11001100. That's address number 1. We'll connect one, one, 0, 0, 1, 1, 0, 0. I feel that it is a pretty loose connection, and that's why maybe the first one was the wrong number here, not 1 but not 0 but 1, because the connection is pretty loose. I will swap this, I think, to this one. So we have now number 11001100, and we want this to be programmed to address number 1, which is now correct, and we disable the output and we enable the writing by connecting this to 0, write enable pin, and to connecting this back to 1. Now we will remove the number from here, and we will check if we have written this number correctly. And for checking, we will enable the output. Take the output and put it to enable 11001100. That's correct. Address number 1 has been written. Now we have address number 2. We connect A0 to 0, A1 to 1. That means address number 2 in binary numbering system. A1 we have 1 here, A0 0, and all the rest are zeroed. That's number 2. At number 2 we have instruction D3, and that D3 D3 means 11010011. So we disable the output. We set the address 11010011. It would be one 1 0 1 1 1 0 1 0 0 1 1. I don't know, this connection is pretty loose. Now let it be. So we have 1 1 0 1 0 0 1 1, and we have address 2. We have this number, and we disable the output, and we now enable the writing, and we disable the writing. We can have this removed, and we'll see the output at address 2. We will enable the output 1 1 0 1 0 0 1 1. That's the correct one, correct number. 1 1 0 1 0 0 1 1 1 1 0 1 0 0 1 1. Number 2 has been programmed. Address number 2. Address number 3, that means A1 is 1, A2 is 1. That's address number 3. All the rest are 0. And at address number 3 we have 56. But we can have whatever at address number 3. It doesn't matter at all, because we are not using this 56. This number is going to sit at the address bus that we are not using. It doesn't matter which port we have here. So we just leave it like it is. It doesn't matter. So we'll take a look at the number 4. Number 4 is 76. Address 4 is going to be 76, and address 4 means A2 we will connect with 1, A0 we will connect with 0, A1 we will connect with 0. That's 1 0 0. Our address in binary numbering system, that's 1 0 0, and in decimal numbering system, that means address 4. Address 4. 1 0 0. It's 1 0 0. That's number 4. It's address 2. That's address 4. 1 0 0. And we have disabled the output. We have disabled the writing, and now we can set that with a number here that we want to write at address 4. That's 76. And that 76 in hexadecimal representation, that means 0111 0110. So let's connect them this way. 0 1 1 1 0 1 1 0 0111 0110 0111 0110. And now we have address 4. We have set the number to be written to address 4. Now we disable the output, and now we enable writing. Writing enabled, writing disabled. Now we will remove the number that we have written, and we'll check how the writing, if the writing has succeeded. So the data bus is free. Now we will enable the output, and we have the number 0111 0110. That's the correct one. And that was the last one, which means stop, halt, don't do anything. So if we have written the program correct, fine. If we succeeded writing the program, then we will have a number, not AB, but we have 1100 1100 1100, as I remember. So we will remove the voltage, we don't need this, and we will check here. In the computer, what we have written here. And this, we will connect the computer with the voltage. Yeah, as you see, we have written this program successfully. 1100 1100 from 7 to 0. So the next thing that we're going to see in the next part, we're going to make some music at the speaker. Okay, thanks for watching, and bye for now.